Section 2.7, Cylindrical and Spherical Coordinates. So before we start this section, make sure, well, like most of what we've done, make sure you have your calculator handy for when we have to evaluate those odd angles. And also have your unit circle handy. I think that's good to have. If you don't have a unit circle, you can always go ahead and Google one and you can find a nice unit circle. Remember, when working the unit circle, your x coordinate is cosine and your y coordinate is sine. And to find tangent, we just use sine over cosine, so y over x. Okay, let's go back to our notes. So what we're going to do in this section is we're going to learn how to go into different types of, I guess we can say perspectives to points. We're going to learn about cylindrical, which we kind of seen, and spherical coordinates. We're going to learn how to go from them, each one using the values x, y, z. There's formulas we use, and I think that's just like the punchline of this section. We're also going to talk about how other graphs behave, but the main bulk is going from cylindrical to spherical to rectangular. All right, let's begin with cylindrical coordinates. And we expand the traditional Cartesian coordinate system from 2 dimensions to 3, we simply added a new axis to model the 3rd dimension. So when we worked with x, y, and then we added another axis z. Starting with polar coordinates, we can follow the same process to create a new 3-dimensional coordinate system called the cylindrical coordinate system. In this way, cylindrical coordinates provide natural extension of polar coordinates to 3 dimensions. The cylindrical coordinate system. Definition. In the cylindrical coordinate system, a point in space is represented by the ordered triple r, theta, and z, where r and theta are polar coordinates of the point's projection on the xy plane, and z is a usual z coordinate in the Cartesian coordinate system. We can go between cylindrical and regular coordinate systems. So we have theorem 2.15, conversion between cylindrical and Cartesian coordinates. In the rectangular coordinates x, y, and z, the cylindrical coordinates r, theta, and z of a point are related as follows. So to find x, that's made up by x is equal to r cosine theta, y is r sine theta, and z, well, z is z. That one stays the same for both cylindrical and Cartesian. To find r is made up of x squared plus y squared. And to find an angle, tangent theta is equal to y over x. And again, z is z. So when do you use these? When you need an r, maybe to go from cylindrical to rectangular or Cartesian, you use that formula. So that's when you need the r value and you don't have one. This tangent theta is helpful when you need to find an angle. Okay, so let's do this example. Plot the point with cylindrical coordinates 4, 2 pi over 3, and -1. Okay, so we want cylindrical coordinates. We're given these cylindrical coordinates and we want to graph them. Well, maybe it is worth our effort to change it to rectangular coordinates and then graph. Okay, so we have our conversion rules right above us. Okay, so we have these values in cylindrical, which are r, theta, and z. We already have z because z doesn't change. We just need to find x and y. X and y. Well, we have a formula to find x right above. To find x, we use r cosine theta. Okay, let's go ahead and do that. So we have r. Well, do we have an r for r cosine theta? We do. That's that 4 from our cylindrical coordinates. So we use 4 times cosine of, we need an angle theta. Well, that angle theta is just the angle 2 square root 2 pi over 3. 2 pi over 3. Okay, so this is why you have how big a unit circle is handy. You can easily see or remember that cosine of 2 pi over 3, well, that's just negative 1/2. 4 times negative 1/2, you get negative 2. That's our x. Okay, now to find y, well, we said that y is made up by r sine of theta. So same numbers, just change cosine to sine, and we have r is 4 sine, and my angle is 2 pi over 3. So I have 4 times square root of 3 over 2. Now notice this is a different number because we're evaluating sine, and sine is at y coordinate. Just refreshing your pre-cal. Okay, so we have 2 square root of 3 as our answer. And lastly, we need to find z, but z is the same, so it's just negative 1. Okay, so we want to go from, we went from a cylindrical to Cartesian. And we did this with the hopes of making it easier to graph. So our answer was negative 2, 2 square root of 3, and negative 1. All right, so now I can go ahead and graph, and we see that we have this point right there. All right, differences between cylindrical and rectangular surfaces. So let's go ahead and go ahead and read this. So the graphs may differ, though they may seem like they're written to be exactly the same thing. Once we graph them, we have to be careful because they will produce different types of figures. Let's consider differences between rectangular and cylindrical coordinates by looking at the surface generated when each of the coordinate is held at a constant. So any number. As long as the number is fine. If c is a constant, then the rectangular coordinate surfaces form x equals z, y equals z, and z equals c are all planes. The planes of these form a parallel to the yz plane, the xz plane, and the xy plane, respectively. Where we convert to cylindrical coordinates, the z-coordinate does not change. Therefore, the coordinate surfaces of the form z equals a number, a constant, are planes parallel to the xy plane. So I have the pictures right here. So this one, this is your z. It's parallel to the xy plane, and that is z equals a number. I think this one is like at 2, so we can say z equals 2. Okay, let's continue. Third point coordinate, the surfaces form z equals z are planes to the xy plane. Okay, we read that. Now let's think about surfaces of the form r equals c. R equals a constant. The points on these surfaces are fixed different distances from the z-axis. In other words, these surfaces are vertical cylindrical cylinders. So we have this picture here. When I have x equals a number, I had a plane parallel to the yz plane. But when I have x equals a number and I have a cylindrical, we're in the cylindrical space, forms not a plane, but rather something like a cylinder. So it's not a plane. Now let's consider, lastly, what about theta equals c? Theta equals a constant. The points on the surface of the form theta equals c are a fixed angle on the x-axis, which gives us a half plane that starts at the z-axis. So we see in rectangular coordinate system, we have this graph, and that would be x, y equals some number. But when we're in the cylindrical system, if I have theta equals a number, it gives us a half plane cutting at the z-axis. Another example, convert the rectangular coordinates 1, -3, and 5 to cylindrical coordinates. Okay, well, we have our formulas in the previous page, right? So our goal here is to go from x, y, z to r theta z. Alrighty. So how do we get an r to begin with? If you recall your formula, we get r from r squared equals x squared plus y squared. Okay, so we have x, y, z. My x is 1 squared plus -3 squared, which gives us 1 plus 9, we get 10. R squared is 10, we take the square root of both sides, we get r is square root of 10. All right, so let's think of what we need. We got x to r, we now need y to theta. Okay, we have a formula to find a theta, an angle. That is made up by tangent theta is equal to y over x. Okay, so I have tangent theta is equal to y, which is -3 over my x of 1. Alrighty, so I need theta is equal to tangent inverse of -3 divided by 1, which is just -3. Okay, we want it in radians. So make sure your calculator is in radians, not degrees. So when we punch this into our calculator, we'll get -1.24. But we want it between 0 and 2 pi. So we need to go ahead and type in your calculator plus 2 pi. Then you'll get our desired result, which is 5.03. And that is our radian. Lastly, I'll let you do this one, z to z. Well, they're the same. So my answer from cylindrical, rectangular, right the first time. From rectangular coordinates to cylindrical, we get the answer of square root of 10 for r. My theta is 5.03 and my z is 5, stays the same. Next example, describe the surfaces of the given cylindrical equations. All right, so this goes with that picture we showed right above of how they may vary. So for our first equation, I have theta equals pi over 4. So we're going to go ahead and know that that's going to be half of a plane. That's going to be half of a plane with an angle of pi over 4. So should have included an image to make it easier. So I have my z, my x and my y. I have an angle of pi over 4, so it's like at 45 degrees. So at pi over 4, and thus creating an angle extending pi over 4, so 45 degrees. Now, if we have r plus z equals 9, and we're in cylindrical coordinates, that gives us a sphere. A sphere following the same circle protocol where we have a radius of 3. So if we have our Cartesian plane, that gives us a sphere. As you can see, I'm not an artist. That's why I always clip snip those functions. All right, and at C, now this is tricky. When I first read this, I read this as Z equals a constant. It's not a constant. It's specifically telling us the value R. Now, when this happens, we're given a Z of 3. Well, not a Z of 3. We're given a Z that they're the same. So, for example, like 3, and R is 3. What this ends up giving us is something like a cone. So if we go ahead and graph it, we're having a cone extending this way and a cone extending that way. These are how these equations translate to the cylindrical equations. All right, so that's it for cylindrical. Let's move forward to spherical. Spherical coordinates. In the Cartesian coordinate system, the location of a point in space is described using an ordered triple in which each coordinate represents a distance. In the cylindrical system, location of a point in space is described using two distances, r and z, and the measured theta. In the spherical coordinate system, we again use the ordered triple to describe the location of a point in space. In this case, a triple of the distance of and two angles. The spherical coordinates make it simple to describe a sphere, just as cylindrical coordinates make it easy to describe a cylinder. Grid lines on spherical coordinates are based on the angle measures like those in polar coordinates. All right, so let's begin the definition of coordinate system. In the spherical coordinate system, a point P in space is represented by the order triple, rho, theta, and phi. So it just explains what each value is or comes from. So the first one is rho, and it looks like a P, and that's the distance P and the origin. Next we have that Greek letter theta, and that is the angle used to describe the location of the cylindrical coordinates. And lastly, we have the Greek letter phi. So on the side I'm reading how I read it when it's pronounced, right? So rho, theta, and last one phi. The Greek letter phi is the angle formed by the positive z-axis in the line segment O and P, where O is the origin and phi is between 0 and pi. All right, next. Theorem 2.16, converting among spherical, cylindrical, and rectangular coordinates. All right, so rectangular coordinates x, y, and z, and spherical coordinates rho, theta, and phi of a point are related as follows. All right, x, y, and z are made up of, so x is x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. And phi is made up of phi squared equal to x squared plus y squared plus z squared. Tangent theta is made up of y over x, And phi is arc cosine of z divided by x squared plus y squared plus z squared, all under the square root. If a point has cylindrical coordinates r, theta, and z, then these equations define the relationship between cylindrical and spherical coordinates. R is equal to R is equal to rho sine phi, theta is theta, and z is equal to rho cosine phi. And rho is equal to the square root of r squared plus z squared, and theta is equal to theta. And phi is the arc cosine of z divided by the square root of r squared plus z squared. Okay, so you have these all handy. I think these are worth to print, maybe cut up, or write on a post-it. Last example, convert the rectangular coordinate -1, 1, and square root of 6 to both spherical and cylindrical. Okay, so let's go ahead and begin with spherical, especially since we have it right above. So we have these values. I always like to mark up what I have. We have rectangular, right? So we have x, y, and z. To come up with spherical, I need to come up with a phi and a theta so that I can use those within my spherical coordinates phi, theta, and rho, theta, and phi. So to begin, just to have a game plan, I want to go to x, y, z, and go to spherical, which is rho, theta, and phi. Okay, let's begin by finding that rho. How do I find rho? Do we have a formula for that? We do, right? Rho is made up of x squared plus y squared plus z squared. So rho squared is equal to x squared plus y squared plus z squared. Okay, we have x, y, and z, which gives us -1 squared plus 1 squared plus square root of 6 squared. So that gives us 1 plus 1 plus 6, we get 8. B squared is equal to 8. So then phi is equal to the square root of 8, which is equal to 2 square root of 2. Okay, now we want to find a theta. So we found x and phi, rho. Now let's find y and theta. Okay, well, we know from the past, and also from above, that theta is made up of, I guess we can write it, so it comes from tangent theta is equal to y over x. Or if you want just theta, theta is equal to tangent inverse of y over x. Okay, so theta is made up of tangent inverse of -1 over -1. And so therefore, we're left with 3 pi over 4. Okay, lastly, we need to go ahead and find my phi, or our phi. Okay, so we have a really nasty formula for phi. Can we use some other one of these, another type of the equations listed to help us find phi using what we have? And we do, right? So I'll write a little note. Instead of phi formula, let's use z is equal to rho cosine of phi, not theta, phi. We have z and we have rho, so we can use what we have to find our last missing piece. So z is equal to square root of 6. We have that value. Phi we found to be rho. I keep confusing rho and phi. Rho is 2 square root of 2 cosine of one unknown, which is phi. All right, so we go ahead and divide by 2 square root of 2, and we're left with phi is equal to cosine inverse of 2 square root of 2 divided by square root of 6 divided by 2 square root of 2, we get square root of 3 over 2. All right, so we're doing cosine inverse. So for that, you look at your answer and you see what degree it comes from. Theta is pi over 6. So again, your unit circle, you see where cosine is this as an answer. You see it comes from angle pi over 6. Okay, so we have all of our values to go from x, y, and z to rho, theta, phi. So rho, theta, rho, theta, phi is made up of, well, our rho was 2 square root of 2. My theta was 3 pi over 4. And my phi was pi over 6. So that was spherical. Now for cylindrical, I want the values r, theta, and z. Okay, well, we already have r. No, we're missing r. We already have theta. Theta's right here. And z, well, z is the same as our rectangular coordinate z. So our only missing value is r. You can use any of your values or equations above to find r. You have about 2 or 3 options to consider. Let's go ahead and use r is equal to phi sine theta, since we have rho sine theta, since we have rho and we have a value theta. R is equal to rho sine phi. Phi. All right, so rho is 2 square root of 2, and sine at phi, which is pi over 6. Okay, so I have 2 square root of 2, and sine at pi over 6 is 1/2. So we're just left with square root of 2. So to have our cylindrical coordinates, r, theta, and z, we just have the values. R, which is square root of 2, we just found. Theta, we found before, 3 pi over 4. And z is the same, so I have square root of 6. All right, that's it for section 2.7, cylindrical and spherical coordinates. Thanks.